Chapter 5, Section 17, inverses. Yesterday, when we were doing our graphs, we were doing this where we were reflecting over the line y equals x. When we do that reflection, we're actually looking at the inverse of that equation, and we want to talk about how we get that. The line y equals x acts as a mirror for a relation and its reflection across the line. When you reflect a relation across the line y equals x, the reflection is called the inverse. The x and y coordinates of each point in a relation are reversed when you graph the reflection. Number 1, you may also graph a relation and its inverse on the graphing calculator. Your teacher will give you instruction on how to graph the inverse with the graphing calculator. Enter the domain of the following data sets, 10 members, into list 1 of your graphing calculator. Enter the range, also 10 members, into list 2. So let's go ahead and pull up our handy dandy little calculator. So the first thing it's asking us to do is in our calculator is enter in the domain into my calculator. So I want to hit stat, go to 1 for edit. Of these, which is my domain, my x's or my y's? My x's. So my x's are 3, 3, 3, 4, 4. 6, 6, 7, 7, 7. My range, I want to enter these into L2. My range are the y's. So that's 2, 3, 4. One, 5, 1, 5. 2, 3, 4. Thank you. Make sure that all my numbers are correct and they're listed in there correctly. Okay. Number 2, examine the scatter plot with list 1 serving as domain and list 2 serving as your range. So let's do this scatter plot. So I'm going to go to second y equals. I want to turn on L1. I want to make sure the type is a scatter plot. So make sure your scatter plot is turned on. The type is the scatter plot, the first one here. The X list needs to be L1. The Y list needs to be L2. And let's do the mark as the little square. I'm going to look at my list and realize my X's go from 3 to 7. My Y's go from 1 to 5. So I'm going to hit window. I'm going to make my X's go from 0 to 10, and my Y's go from 0 to 10. So that when I graph, this is the picture that I get. I just gave away Alex's calculator. That was mean of me. That's yours. I don't know. Kaylee. Actually, it's that one. With no sticker on it. Sorry. Okay, everyone else have a calculator following along, please? Please. Randy's a nice guy. He'll share. Scoot together and make sure you can do this. Okay. Examine the scatter plot with list 1 serving as domain, list 2 serving as range. Okay. We can do that. Yay. Then activate a second scatter plot with list 1 acting as range and list 2 acting as domain. I'm going to pause this real quick. Click on window. Please make your window match this. Let's do 0, 12, 1, and then 0, 8, 1. Of course, that wasn't a 0. So make sure your window matches this. Hit graph, and it gives you more of a circle. It's not as much as an oval, it's more of a circle now. Okay? Okay. Then activate a second scatter plot with list 1 acting as a range and list 2 acting as the domain. So come back over here, hit second y equals, arrow down to number 2, hit enter to turn it on. Type, I want to be as a scatter plot, my arrow down, my list. I want my X list to be L2. So we're going to hit second 2 for X list to be L2. Arrow down, hit second 1 for Y list to be L1. Arrow down, make sure the mark is the little plus sign. Why did I switch my L1 and my L2?
We're going to put in more data.
Nope, I'm not going to put in more data. For the inverse, everything we've been doing over the last 2 days, we switched my X and my Y. I switched my X and my Y. So that's what we're doing here. We're switching my X's and my Y's. Hit graph. And this should be the little picture that you end up with. Okay. It then says for number 4, okay, but you should have them both on. So hit go back, turn on L1 and L2. Okay. Number 4 says graph the line y equals x. So I'm going to go back to my calculator. I'm going to hit y equals, and I'm going to make y1 equal to x. And if I go ahead and graph this, what do you observe? It's symmetrical around that line y equals x. It's symmetrical. I get that reflection. Okay? Turn to the notes section of your notebook. Get out a sheet of paper, date it March 15th. Beware the Ides of March. According to Shakespeare, it's the day that Julius Caesar was killed, but that's a different story. Beware the Ides of March. In your notes section, I need you to go in there and find, we're going to do notes today, March 15th. I just need you to write down this information and to check this box. These are notes we need to know. So please write these down. I will pause the recording. So the notes do say the inverse of relation is a reflection of the relation over the line y equals x. When a relation is reflected over the line y equals x, the x and y coordinates of corresponding points are reversed. The domain of the relation becomes the range of its inverse, and the range of relation becomes the domain of its inverse. All relations have inverses. The term inverse is used 2 ways in mathematics. One to describe an opposite operation, the other to describe a type of relation. To go along with this, remember, it's been a while since we talked about relations. A relation is just sets of ordered pairs. There's no rules on those ordered pairs. So when we started this section back over here, this here is a relation. This set of numbers, this set of ordered pairs is a relation. We're not putting any type of rules on that set of numbers. It's just a set of ordered pairs. That's why we call it a relation. Okay. So on the next page, think it's on the next page. An inverse reverses or undoes a previous action. A pitcher throws a ball, the catcher catches it and throws it back to the pitcher. Taking your shoes off and putting them back on is an example of an inverse. If you graph a relation, reflect it over the line, y equals x, and then reflect it back, you will have the original, the same relation that you started with. Number 5, where in mathematics have you used inverse operations? We're pausing for people to give answers. Parabolas, explain. Seth doesn't know how to say the word parabola. He likes to think it's a parabolas. I don't know what a bola is unless you're talking about bolo tie, but that's a bolo and not a bola. But a parabolos just doesn't make sense. Well, you are a parabolas.
I don't know what that means.
Exactly. Neither do I. But I know what a parabola is. Exactly. A parabolas. All right. So, where in mathematics do you see inverse operations? Mr. Seth says in parabolas. I don't know where he sees that. Where do you see that? So what are inverse operations? If I give you 2x plus 7 is equal to 13, and I said to solve for x, what would you do? You would subtract 7 and divide by 2. What is subtracting by 7 and dividing by 2? Those are the inverse operations. That's what we're talking about here. When you subtract 7 and divide by 2, those are inverse operations. So number 5, write down something for those inverse operations. Like that example I wrote up there, 2x plus 7 equals 13. Subtracting 7 from both sides is inverse operations. Dividing by 2 to both sides is inverse operations. Taking the square root of x squared is an inverse operation. Yes, Mr. Randy? 5 is the first thing you're writing because 1 through 4 was just calculator stuff. 1 through 4 was just calculator stuff that we just talked through. So you're writing down something for number 5. I'm going to pause. Number 6, not every action can be reversed. List some examples of actions that cannot be reversed. The first thing I thought of is our good old buddy, old pal Nathan over here, purposefully had his earphone in his ears so I can bring out my scissors and start talking about, yes, I'm going to cut his ear off. No! And talk about inverse operations or not having an inverse. If I was to cut his headphones to make a point that he shouldn't have it in his ear, is that reversible? Well, you'd have to try to splice wires and stuff, and that would be a pain, and you'd probably end up shocking yourself or something worse. That is not reversible. That is not reversible. Cutting something usually is not something you can undo. Alex is going to let me show you how this works right here.
Indeed.
All right. What are other examples of things that cannot be undone, that cannot be reversed, that cannot be inversed? What do you think? The Constitution. You love being abstract with answers. You try to think of the most outlandish thing to say, and you say it. What's something else that can't be reversed?
Your hair, it can't grow back.
Smash a watermelon on the ground, can't put it back.
If you smash a watermelon on the ground, I don't want to even think of what you would have to do to try to put it back together. That is something that cannot be reversed. I agree. If you are in the middle of a musical set and you go crazy and you smash your guitar against your amp because you think the drama of it would be so cool, You can't undo that. You have to go buy a new guitar. If you did it yourself, that's your own choice. So please write something down for number 6 as something that cannot be undone. List some examples of actions that cannot be reversed. Those are real practical things. Linear functions can be reversed. They can't. There is an inverse to it. We will work on that in a little bit, I believe. Like I just said, number 7, graph f of x equals x squared. Graph the inverse. List 5 points from each graph in the table. On your paper, please draw an xy axis. Let's draw the graph f of x equals x squared. So, I'm going to go ahead and pull up some graph paper. Please draw an XY graph. Like we were doing yesterday, negative 10 to 10, negative 10 to 10. Doesn't have to be that big. Doesn't have to be that big. That's perfect. It's just a little square that we can kind of do some points on. Okay? Okay. So this is the graph that I'm going to use. I'm going from negative 10 to 10, negative 10 to 10. Doesn't have to be huge. I just need to graph this. Now, do understand the book is making a huge distinction right here. The book is not saying y equals x squared. They're saying f of x is equal to x squared. They're telling us that this is a function. Remember when we talked about this yesterday, a function does not repeat any x's. If I did a vertical line test, if I drew a vertical line, it would only touch the function once at a time. So function f of x is equal to x squared. When we did this yesterday, we picked the points negative 2, negative 1, 0, 1, and 2. We actually did stick in negative 3 and 3. Instead of doing x and y, I'm going to do x and f of x. So if I square negative 2 squared is 4. Thank you, Miss Justine. Negative 1 squared is 1. Thank you, Miss Kaylee. 0 squared is 0, 1 squared is 1, 2 squared is 4. How nice. Plot the points. Negative 2, 4. Negative 1, 1. 0, 0. 1, 1, 2, 4. This is my parabola. Keep your parabolas to yourself. All right, so I have my parabola. Okay, remember, if this is my original function, if I wanted to do an inverse of it, what would be my x's and my y's? 4 goes with negative 2, 1 goes with negative 1, 0 goes with 0, 1 goes with 1, 4 goes with 2. So I have 4, negative 2, 1, negative 1, 0, 0, 1, 1, 4, 2. My parabola, my parabolic shape would look like this. Okay? So this is number 7. Number 7 says to do the function f of x is equal to x squared. It says to graph the inverse. We've done both of those. It said list 5 points from each graph in a table. We've done that. Okay, so this is number 7. So, number 8 asks the question. For number 8, I need a vertical line, so there's my vertical line. Number 8 asks the question, is f of x equals x squared a function? Meaning, if I move this vertical line across my graph, the black graph, will it touch it more than once at a time? The black graph? Not the black graph. It only touches the black graph once at a time. So that tells me that the original f of x equals x squared is a function. Number 9. Asks for the domain and the range of the original function. F of x equals x squared. What can I plug into this x? Are there any x's I cannot plug into that x? No, I can plug in any number I want. So my domain is x is an element of all real numbers. X is an element of all real numbers. I can pick any number I want to be my x, and it's going to work just fine. My range asks the question, what y's is this graph going to give me? If I plug in -3, -4, -50, -1,000,000, +1,000,000, I plug in all these numbers, what y's is it going to give back to me? Is it going to give me back every single number? If I'm looking at just the black graph, it's going to give me all my numbers that are greater or equal to 0. It's going to give me numbers that are only above that green line or on that green line. So my range are y's greater than or equal to 0. It's never going to give me a point that's a negative for a y. They're always going to be above that green line. And now I'm going to take out that green line. For the domain, I wrote x is an element of. It's a weird circular type E that stands for is an element of, is a part of. And then I wrote what we called a bold R, which stands for all the real numbers. X is an element of all real numbers. That's what I wrote for the domain. The range is y's greater than or equal to 0. And I'm going to get this out of the way for our next part. Number 10, the first thing they asked us, now that we looked at the original function, number 10 asks us, is my inverse a function? If I take this black vertical line and move it over the blue graph, do I hit the blue graph more than once at a time? The answer is yes. So number 10 asks, is the inverse a function? So the answer to number 10 is no. The inverse is not a function. Number 11 asks, what are the domain and range for the inverse? What are the domain and the range for the inverse? you just pretty much switch the answer from number 9. The domain is talking about x's, but I'm going to want the x's that are greater than or equal to 0. My range, I want to want the y's that are an element of all real numbers. That's my domain. That's my range. Okay?